Okay, in this video, I'm going to look at several examples involving the position vector xi plus yj plus zk. Of course, alternatively, we can write this in this notation. So that is the position vector xyz, and this here is its magnitude. So just the square root of x squared plus y squared plus z squared. So we're going to look at examples of quantities involving grad, divergence, and curl of different functions that can be formulated using these two, the vector here and the magnitude. In the first example, for instance, the grad of r squared. So since r is the square root of x squared plus y squared plus z squared, then r squared, so grad of r squared is simply going to be grad of x squared plus y squared plus z squared. So remember, grad is a vector, so the x component of this vector is going to be the derivative of this function with respect to x. So that's going to be 2x, and then the y component is the partial derivative of this function with respect to y, and similarly the z component is the derivative of the same function with respect to z. Now we notice that 2 is common here, so if we factor out 2, and then all of a sudden you can see that this is 2 times the position vector r. So that is going to be the gradient of r squared. In part B, we are looking for the Laplacian. So it's a bit, if you like, similar to this one, but the grad is squared while the r does not have power 2. So so what's going to have happen in B, we're looking for the Laplacian of r. So the Laplacian is going to be the second order derivative of r with respect to x plus the second order derivative with respect to y plus the second order derivative of r with respect to z. Now, since r is symmetric, we are going to use that fact, and so we'll just do the x derivatives here, and then we'll be in a position to infer what the other derivatives are going to be. So let's start with the first order derivative. So this is r, first order derivative with respect to x. So this is the same as the derivative of x squared y squared plus z squared to the power 1/2. So if we multiply by 1/2 and then subtract 1, and then derivative of this thing with respect to x is going to be 2x. So that means this thing is going to be x over the square root of x squared plus y squared plus z squared to the power 1/2. So that is the first order derivative. Then the second order derivative is simply going to be the derivative of this thing here. So that means we are now going to have to use the quotient rule. So if we do use the quotient rule, this is going to be our u, and this is going to be our v. So remember, in the quotient rule, we have u prime v minus uv prime all over v squared. Now, the derivative of u is going to be 1, and v is x squared plus y squared plus z squared to the power 1/2. And then now we multiply by u, and then derivative of this we've just done in the previous line. Derivative of this we've done here, and it's given by that. So it's just going to be x times x over x squared plus y squared plus z squared to the power 1/2, and then this is all going to be divided by v squared. And then so this is going to be x squared plus y squared plus z squared to the power -1/2. Take away x squared over x squared plus y squared plus z squared to the power 1/2, then all divided by x squared plus y squared plus z squared. Now if we write the numerator as a single fraction, let's say over 1 here, and then write this as a single fraction. So this is what we're going to have. The LCM is going to be x squared plus y squared plus z squared to the power 1/2, and then 1 is going to go here this times, and then this times this is just x squared plus y squared plus z squared, and then this goes here once, then 1 times x squared is just going to be x squared. And then remember this term is still here, so I'm going to write that one there. So if we simplify here, notice that this is going to cancel out, so we're going to end up with not x squared, y squared plus z squared, all divided by x squared plus y squared plus z squared to the power 3/2. So that is going to be the second order derivative of r with respect to x. Now, using that property of symmetry that I talked about, so you can see that here if we differentiate r twice with respect to x, we get this. So if you differentiate r twice with respect to y, you can see that here what we have is just r squared but without the x term. So instead of x squared plus y squared plus z squared, we just have y plus z squared. So similarly here we are not going to have the y term in the numerator, so we're now using that symmetry property. And then for the z term, there isn't going to be a z in the numerator, so it's going to be x squared plus y squared, but the denominator is going to be the same in all three cases. So that means so the Laplacian of r is the sum of these three. Okay, so it's just going to be this one plus this one plus this one. So if we do that, we can see that from the first one we've got y squared plus z squared. From the second one we've got x squared plus z squared, that's here. So x squared plus z squared, and then the last one we've got x squared plus y squared, all of them divided by x squared plus y squared plus z squared to the power 3/2. So if you look at the numerator here, we're going to have 2 of these, then 2 of these, so we're going to have 2 of each. There's going to be 2 into x squared plus y squared plus z squared, all divided by x squared plus y squared plus z squared to the power 3 over 2. So if we simplify this, there's going to be 2 over x squared plus y squared plus z squared to the power 1/2. So that is simply 2 over r. So that is going to be the Laplacian of r. Okay, then in part C we have the curl of r times the position vector r. So the first thing we need to do here is work out this. So what's going to be r times r? So r times r, so this one is x squared plus y squared plus z squared. This is a scalar, then we're going to multiply it into that vector there. So that is going to give us, so we just multiply all the components here by the same scalar. So we're going to have x into x squared plus y squared plus z squared, and then y into the same thing, and then z into the same thing. Okay, so I'm just going to do that for that same term there. So that is going to be this vector here, r times r. Now we want the curl of that. So the curl of this is going to be, so we've got here I, j, and k, x partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Then here we're going to have x times square root of x squared plus y squared plus z squared, y times square root of x squared plus y squared plus z squared, and z times the same thing. Okay, now so for the first term, for the x component, it's going to be the y derivative of z times the square root of x squared plus y squared plus z squared. Take away the z derivative of y times the square root of the same thing. So that is the I component. So that's the y derivative of this minus the z derivative of this. Then for the j component, it's going to be the z derivative of this. So z of x times the square root of x squared minus y squared. Then the x derivative of this one. So z here times that, and then lastly it's going to be the x derivative, so it's this one here, the x derivative of this one minus the y derivative of that one. So it's going to be x of y times the square root of x squared minus y plus y squared plus z squared, and then y x into that. So all the square roots are square roots of x squared, square roots of x squared plus y squared plus z squared. So again, we're just going to work this one out and then use the symmetry property to infer the others. So what's going to be the y derivative of z times x squared y squared plus z squared? Now if you look at this, there's only one term involving y here, so there's no need to use product rule. So we just use chain rule here, multiply by 1/2. So we're going to have z into 1/2, then x squared plus y squared plus z squared to the power minus half, and then times 2y. and then the half and the 2 will cancel out, so we're going to have yz all over the square root of x squared y squared plus z squared. If you like, this is the same as yz over r, because this is just r. So this term is going to be yz over r. Similarly, this one is going to be zy over r. This one is going to be xz over r. This one is going to be zx over r, and then xy over r, yx over r. But then these two are the same, so that means we're going to be getting 0 in each case, and so this curl is going to be equal to the 0 vector, so 0, 0 and 0 there. So that was example number C. The next example is D. Just check these out. So in D we have the divergence of vector r divided by the magnitude of vector r. So that's actually going to be a unit vector. So we have the divergence vector r divided by the magnitude of r. So again here, vector r divided by r is simply going to be x, y, z here divided by x squared y squared plus z squared. So this is going to be x over x squared plus y squared plus z squared, square root of that, y over square root of that, and then z over the square root of that, y squared. Now the divergence is a scalar quantity, and it's going to be given by the x derivative of the x component plus the y derivative of the y component plus the z derivative of the z component. So here we're just going to have to do the x derivative of the x component. However, we have already done this one here in a previous exercise. So derivative of this, I'll just show you, we did in this example here. Where is it? There. Okay, so x derivative of this term, we worked it out, it's equal to that. Okay, so that's simply going to be x squared over y squared. Just one moment. So this is going to be y squared plus z squared all divided by x squared plus y squared plus z squared to the power 1, not to the power 3 halves. Okay, so that means the divergence of r vector over that magnitude of r, the first term is going to be y squared plus z squared over this term. The second term is going to be x squared plus z squared over the same term, and then we're going to have y squared plus x squared over this term here to the power 3/2. And then we've already worked this out to be equal to, so if you cancel out here, this is going to be 2 over x squared plus y squared plus z squared to the power half. So this is 2 over r. It's the same answer that we got for the Laplacian of r, which was here. Right, so that is that. We're not going to give you a few minutes to have a go, moments to have a go at the remaining exercises. So if you just want to pause the video, then when you continue with the video, then you can compare with our solutions. Just want to have a go at E, F, G, H, and I. All right, we're now going to scroll down to our solution of E, F, G, H, and I. So for E, we just have the divergence of the position vector r. So it's just going to be the derivative of this with respect to x, this with respect to y, this with respect to z. So it's just going to be 3. Then here we've got the divergence of this vector here. This vector, if you multiply the vector r by the position vector, this is what you're going to get: the x component, y component, the z component. If we just differentiate this one with respect to x, this is what we find. So using the product rule, then writing this as a single fraction, it gives us that. So that means for the y component, the 2 is going to be on the y. For the z component, the 2 is going to be on the z. If you add these, you're going to get 4x squared plus 4y squared plus 4z squared. So this is going to simplify to 4r. And then gradient of 1 over r, so we just differentiate this once with respect to x, we get this. So it means if we differentiate it with respect to y, going to have minus y and then minus z for this one. So here we have got the x, y, z vector, which is the position vector with minus outside. This is just a scalar. The scalar is r cubed. Then for the Laplacian, so just working from this one, we just differentiated this once with respect to x. So if we differentiate this again with respect to x, which we do here, then using the quotient rule, this is what we get. So, and then we're going to do the same thing with respect to y. So if we got 2x squared minus y squared minus z squared, for the y1, the y will be here, and then for the z1, the z is going to be there. Now if you remove brackets here, then the numerator works out to 0, so it means the Laplacian of 1 over r is 0. Then the curl of r squared times r, that is going to be r squared times r. If we multiply this into the vector, these are the components, and then we plug these into the 3 by 3 determinant. So here, a derivative of this with respect to y is simply going to be 2yz. This with respect to z is going to be 2zy. Similarly for the others, and so this is going to give us a 0 vector. Okay.